All right, so we're on page 371. How about we've got a 1,700-pound beam being held up by the pulley. Let's draw a free body diagram of the beam and also a free body diagram of the pulley. Okay. So let's kind of focus on the difference between drawing free body diagrams for different things. So one free body diagram for the pulley, the other for the beam. The other thing is, free body diagram's kind of a lot to say, it's a lot to write, so it's commonly abbreviated just FBD for free body diagram, okay? So how about getting a free body diagram of that drawn, both the pulley and the beam? I often do them right on the sketch rather than making a whole new sketch, so that's commonly how I do those because it's just faster to do, all right? And sometimes we like to get through things.
No, you draw it on the thing. You said from point G, like that's the center.
Yeah, G is the center of gravity, right?
374.
So, yeah, that's a good point. G is the center of gravity. That's the point to which you put the weight on G. That's the general rule. G means center of gravity. That's where the weight would act. You can kind of think of the weight of that beam as being like a distributed load. G is the centroid for the beam. So you can put the load right there at that point. So page 371 is where we're at. Does that work better? Or,
yes.
It does? Okay. So you can still write. Okay. We also like to get the angles, so do the trig there to get the angles. That's typically what I'll do that on a free body diagram. If they're not given, I'll calculate them. You do, because angles are an important part of solving out problems, so I want them on the free body diagram. So we got to run it that. We got anything going with that? I do find it helpful to draw a boundary around whatever it is I'm trying to draw a free body diagram of. That helps to identify any of the contact forces. Because anything you cut through with your boundary, that then has to be shown as a force on your diagram. Okay. So if I want a free body diagram of the pulley, I'll draw a boundary around it. If I want a free body diagram of the beam, I'll draw a boundary around it like that. That's often how I start. It's funny, just doing that, obviously you can just kind of look and see those things, but just drawing that boundary helps to point them out. You don't tend to skip over them carelessly when you draw the boundary, because now you start seeing, oh yeah, I cut through this or that. Okay. Good. I got something like that. You see my boundaries that are highlighted. We doing all right with that? The thing I point out, you got the weight of the beam at the center of gravity that's going down, obviously. Then you got the two cables on the beam holding it up. Then the pulley has three cables. That top cable, I could pretty well quickly figure out that's 1,700 pounds. You don't have to put that on there, but I could just see it. That's what it would be. The thing I want to point out here is the cable directions, okay? That we're kind of drawing free body diagrams of different things. So we want to show what the cable does to the thing you're drawing the free body diagram of. So this cable here is pulling up on the beam at a 33.7 degree angle. I did the trig over here. Okay, the cables pull up on the beam. Because cables are, remember, they're only in tension, they pull is what they do. The cables pull down on the pulley. So they pull up left and up right on the beam, and down left and down right on the pulley. The key word there is in both sentences, I said the cables pull. Okay? So what we're finding here is those cables have a force of tension in them. They're pulling on both objects. So which way they act depends on what you're drawing a free body diagram of. If you're drawing a free body diagram of the beam, they're pulling up to the up. If you're drawing a free body diagram of the pulley, they're pulling down. Y'all okay with that? We got any questions on that?
How do you feel about the dot style free body diagrams, like a physics class?
I don't do dots. Sorry, I'm sorry. You could tell I have a little reaction to that. Yeah.
No.
I'm sorry. I didn't quite. I'm sorry. The reason I have a reaction to that though is that just breaks down totally in what we're trying to do. And
it still shows the angles and the, but that's fine. No dots.
Don't go there. Just don't do dots. We don't. Yeah, just.
I thought about it.
Okay. Yeah,
I might have turned into homework like that if I hadn't asked.
Yeah. Okay. Well, we're getting a little reaction out of me, obviously. Now, there are some things that you learn in physics that transfer to the classes I teach. There are other things that do not, okay? And dots don't, okay?
I mean, the math, I could draw 3 dots, or I could draw 1 dot, and just that angle and that angle. You know what I mean? They're the same, but yeah.
You could do an impressionistic sketch of the forest in France, too. You can do that. You can do a lot of things. You can draw lots of things out there. However, what I like is a picture of the object. As an engineer, I want a picture of the object. And the reason I don't like dots is this 6 feet and 6 feet matter, okay? And I think in physics, what you do, you cover 100 topics, not very deep. We're drilling down into some topics very deeply. And dots work fine in physics, of course. That's why they do that. But in here, we have objects with dimensions, and so dots don't work well. Okay. And you run into other couple things that with me, maybe not in this class so much, but if you take dynamics from me, there's some things that are done in physics that don't transfer well to how we do it in dynamics. Okay, so we do want the objects drawn.
Is that, I have a question.
Yeah.
So since the tension in is the law of the pulley and the weight, the tension is the same, all tensions are the same.
Right. Well, yeah, right. In those angled cables, you're right.
Yeah.
All those tensions would be the same, right? So that's why I put one variable on them. The variable is T. Everyone's marked T, so I can solve once for a T, and I've got it for every one of them. Okay. All right. Other questions?
I don't remember from when I did physics, but is there you draw gravity force on the pulley?
Okay, the weight of the pulley, you mean, or
What was that?
like the weight of the pulley, or when you say gravity force, do you mean like the weight of the pulley?
Yeah.
Sometimes we'll ignore the weight of things if they're small and not significant. So the weight of that pulley I'm ignoring. And usually it's in the problem statement that should be addressed. I don't know if I did it real well on this one, but what I'm thinking here is compared to a 1,700-pound beam, the pulley would be pretty negligible, and that's why I'm not putting it. Other questions? This is all good because this stuff, it's important to do this, and get it right and figure out the conventions and all that. You need a good free body diagram to solve a problem. Okay. All right. Other questions? Are we good? All right. So let's see. Now, another thing I point out here is pay attention to the sentence. The typical phrasing is draw a free body diagram of. And the thing that comes after of is what the free body diagram will be. Okay? So that will be a free body diagram of the lever. Okay? So usually I just do it right on the sketch because it's quicker and easier. But if I didn't, this would be what I'm drawing the free body diagram of. So keep that in mind, what you're drawing a free body diagram of. And this kind of gets back to that previous question. You know, I can't make that into a dot. Okay, that one. You know, I'm kind of focusing on this, but you know, that's obviously not a dot. It's got a length. The dimensions are very important in solving it. So that's, you know, why I don't draw free body diagrams as dot. That's a very good example of one that just wouldn't work. All right, now the key to this is we're assuming there's some wording here, and it's just kind of standard wording. On this one, the phrase there is assume friction is equal to 0. Another term you see for that is the word smooth. That means, what that means is mu is equal to 0, okay? So if you see the word smooth, that means that mu is assumed to be 0. Now, of course, mu is never 0 that I can ever think of. But keep in mind, when you're doing engineering analysis, you can only handle so much stuff. I mean, you know, I could design a bridge and account for the gravitational effect of Saturn orbiting around the Earth on the bridge, but it's not worth it. It's too complex. I don't do it, right? It doesn't make enough of a difference. So keep in mind, all this modeling we do as engineers, we simplify things so we can handle the models, okay? Then to compensate for it, what do? We throw safety factors on our answers, okay? That's kind of the process, okay? So anyway, so we're assuming that this is smooth, no friction. Now, the important thing I want to get at on this is the direction of the forces. That's going to be the key thing on this one, is to get them going the right direction.
Assuming the board has weight?
That's a good question. If I don't see any mention of it, I'd assume it's negligible. Okay, and that's just a convention in how the problems are written out. So if no weight is mentioned, you typically assume it's 0. And a 0 assumption means you're assuming the weight of the lever is not great compared to some of the forces that are being applied to it.
There's a force pushing up right here.
Okay, now just pay attention to the direction of your forces. What's the rule on smooth contacts like that? The force is what? There's a little wording we used on that I had?
Is the lever?
Maybe on the previous page or two on that typed out list I had stuff. Normal, yeah, to the flat surface, right? Yeah. So the forces are normal to the flat surface is the way that's expressed. Okay, that's the key on being able to draw the forces going the proper direction. And I think on this one, the thing to figure out is what is the flat surface, okay, as you're doing.
If we were to do both surfaces, there could be 2 normal forces.
What's that?
Are there 2 spots where there could be a normal force?
Yeah, B and C, I think. Okay. All right, so the key thing on this is identifying what the flat surface is, and it changes depending on where you're looking on this one, okay? Okay. So here, I think the board is the flat surface. But on that fulcrum where the lever is going around, this flat surface is the lever, see? So we want to identify where those flat surfaces are and then show the forces acting. Okay, so at C, I think we got a vertical force. And everyone just think about it for a second. Is that vertical force at C going to go up or down? Just think about it. Okay. And the answer to that question is, what am I drawing a free body diagram of? The lever.
It's pushing up, but the normal force is going to be pushing opposite the lever,
Right.
right?
I'm putting the force on the lever. Okay. And this is a typical one because you kind of say, well, that lever is pushing up. Yeah, it is. But I'm drawing a free body diagram of the lever, so I'm looking at what the board does to the lever. Okay. It pushes down. Okay. So we want to keep that stuff straight. Although I will mention that even if you guessed you got that incorrect and you had this going like that, you'd get a negative answer when you solve for it. It wouldn't be a big deal. You just turn it around. Okay, but what you cannot do, you can't have a force like this. If you guessed the force was doing that or even this, you would not get a right answer. You just wouldn't get a sign there you had to flip around. You'd get an incorrect answer had you assumed that, because the force has to be normal to the flat surface. So it has to be a vertical force.
Established your axis along the line of the thingy, right? If you cause your x-axis at an angle, then it might come out okay.
No, it has to be a vertical force regardless of how you set the axis up. Okay? So it has to be straight up and down. It can be up or down, but it can't be at an angle. It won't come out right if it is. Okay? The same thing with RB, okay? RB has to be on that angle, flat, perpendicular to the flat surface. So are we good with that? Okay. And again, if I had RB and I guessed it like this, that would not be a problem. That would still come out right. I would just get a negative answer. It's kind of like, remember doing those dot products? I mentioned that, what the dot products do. A negative answer on a dot product is not a big deal, okay? But now, had I assumed that force to be doing this or that, that would not work out, that you would not get a correct answer out of that. So you do want to get the things at their proper orientation. Okay. I also like to get these angles. So what's that angle right there for RB? Whenever I'm looking at angles, I do right triangles, okay? Now let's see, where's my right angle there? It's between, if I could get my eraser to work, there we go. Right angles between RB and the lever, right? That's a right angle. Yeah. So yeah, this 90 minus the ramper, in this case lever angle is the way to go. That'd be 54 degrees right there. And you often want to have that in there on a free body diagram. On your homework, I want you to dimension the angles. Okay. Okay. We're good with that? All right. Okay, here's a little monkey bar here. I got a little zoom in on the connections. Why don't you draw up a free body diagram of that real quick? This isn't in the book, so just draw a free body diagram and just a quick exercise. How would you draw that up if you're going to analyze the monkey bar? Let's have a child about a quarter of the way across. So we'll put the child right about there. Okay. Now, one of the things on these free body diagrams, don't think too much. If you see a connection, identify the connection type and put forces on the object that reflect the type of connection. What the forces do is they prevent motion. So what you'd want to be doing there is you'd want to identify the connection types. What this is a blow up of that connection and that connection. What is that? Okay. And once you know what it is, model it at those locations. Don't overthink it. You know, if you can identify that connection type, there's a force pattern that we associate with that. Just put it right on the connections. Put a force for the child there as they're working their way across the monkey bar. Then you're good. Okay.
Well, no, because
It could be any degree we want. Normally, X and feedback, I don't have a good reason not to use X.
you're right. It's a normal force thing.
Yeah, there's a potential for a force. Yeah, or up or down. I mean, probably up, force coming down, the support will push back up.
Just try to little bracket. Just like,
Wouldn't it be the force of the bar pushing down, but then the force of the normal force of the bolt pushing on the bar, like pushing back up?
yeah.
So you're doing what's happening in the bar.
Just bar up.
Actually,
Y'all got a little something on that? So what kind of connection is that? Pin joint, right? Now what sort of reactions do a pin joint create? To figure that out, look at the motion that the pin joint prevents. The pin joint won't allow that thing to move left, right, correct? Because there's a pin in there, right? You okay with that? So up we go, like that. Will the pin joint allow motion left and right? It won't. So there has to be a force to prevent motion. Forces prevent motion, okay? Will one pin joint allow that thing to rotate?
Yes.
It will. So there's no moment reaction on a pin joint. There's two forces, perpendicular. What's that now? We good? Okay. Now there's also the weight of the child on the monkey bar. Though if you ever watch kids on monkey bars, that force is probably going all over the place, right? But we'll just say it's down. We'll say they're just hanging there. Okay.
what would you call the forces that are being applied on the pin?
Usually I just use R. I give them letters. I mean, it's not, I'm not so concerned with the name. I'd probably call it RAX. I'd call this point A, RAY. They're reactions is what they are. They're reacting to the forces that are applied to the bar. So they're reactions. I call this B, I'd call that RBY and RBX. And then this would just be the weight. I mean, I don't know if that's answering your question. Okay. So it'd be something like that. And the thing is, don't overanalyze it. You see a connection, replace it with forces. The analysis comes after you draw the diagram. Now, probably in this condition, RAX and RBX are going to be 0. It's probably when I solve them out. That's probably what they're going to be. But the potential for them is there, so I show them on the diagram.
Right, because it's an arch, so it has to redirect most of the energy down. So it's not going to be that much side-to-side motion. So RAX and RBX, they're really small units.
Yeah, and I also think, given that free body diagram, when you solve that out with statics, although it'd be hard to solve with statics, actually it's something called statically indeterminate, but I think RAX and RBX are essentially 0, because there's no active applied force.
Yeah.
So they'll 0 out.
Yeah, it's static, the way that it's shaped, yeah.
The shape, though, doesn't have anything to do with it. Even if it was shaped like this, it would well, I have to be a little careful here. If it was a solid material like that.
Yeah, if it's something that didn't flex, then either way,
Yeah.
Right. At equilibrium, the kid's weight's going to be equally distributed. Yeah.
Right, so that's the key thing there. If it's a rigid body, if it doesn't flex, that would be just an upward reaction at A and B. Okay. We good with that? All right. Okay. Okay, here's an oil derrick used to pump oil. Okay, that thing's gonna rock about that joint in the center. A little zoom in on that. If you ever seen these run, they kind of tip back and forth about this point here. They kind of rock back and forth. Look at what's happening here. There's kind of a cable, and then we've got, looks like a linkage kind of system there, I guess. I don't know. But let's get a free body diagram of that object. So I'm going to outline in red what we're going to create a free body diagram of. Again, this isn't in your book, so it's just a, let's see, I guess we got a little extension down there, don't we? Be something like that. So if you're going to draw a free body diagram of that top object, what's it going to look like? Given what you're seeing, given the applied forces there, how that thing is mechanically put together.
Are those things like train wheels? You know how
Oh, yeah, that offset kind of thing? Yes. Yeah, right. They're powered over here. There's a motor and that kind of, right, it's like a train wheel and how it powers that. That's a stiff linkage, so it can push and pull both. Yeah. Right.
Wait, what did you circle?
Oh, I just circled that one joint there. The old derrick kind of rocks about that point. It rocks there.
Looks like being a drinky bird.
Yeah, that's not, that's it. It's like the fulcrum there. Okay. So what I'm trying to get at here is some of the objects to get to those pictures you see in a textbook. I mean, what are those things? What's the connection on the left? What's the connection in the middle? What's the connection on the right? What are they? How do they act? What kind of forces do they exert? Okay, something like that's what I came up with. You might have come up with something a little different. That's fine, but the main features here is that's a cable that's going to pull down. Okay, that's what connects down in the hole that's been drilled down in the well. Okay, being as it's rocking about this point, that's going to be a pin joint there. So you're going to have an X and a Y. On the right there, you had a linkage. Okay, so that's going to pull down or push up. It could do either. And then you have to account for the weights. And I would break this into two pieces. The head, I would make one piece because I would probably find its center of gravity, and then a beam, a second piece. You might have some variations on what I've got, especially in how you handle the weights. But the thing I would like to make sure you're getting is that's a cable that pulls. That's a linkage, so the force in the linkage follows the direction of the linkage. It goes from one link to the other. That's how the force goes. And then this is a pin joint because the object rocks around the pin joint.
What is
R means reaction, it means the reaction force. So I got CX and RCY. I kind of highlighted over the RCY.
We don't care about MG,
MG is the weight.
that's what RAY is.
No, the weight is here and
What's your weight?
there, WB. I don't use MG, I just call it weight
Wait, okay.
in this class anyway. In dynamics, I might get more into MG, but.
Okay, and then at point B, did you say that could be either going up or down?
Point E, let's
Point
see,
D.
D. Yeah, that could be going, my assumption is, given the angle of that thing, it's probably pulling it down right now, but you could show it going up as well. The important thing is that it follows the line of the linkage from one link to the other. It could be up or down. You could draw it either way. You'd prove it out when you ran the numbers. It would come out to be a positive or negative answer.
Shouldn't there be like no X, the RCX?
Okay, yeah, that's a good point. Now, that's a good point worth kind of bringing out. I think RCX is going to be 0.
Right.
But I think in this stage, I draw it there because I have a pin joint. There is a potential for RCX. When I run the equations, that's when I'll prove it's 0. When I draw the free body diagram, there is a potential for an X force there. I'll show it there. The analysis comes next.
The potential would be in both directions, though. wouldn't it?
Correct, yeah. I guess one or the other, and my signs will prove out which way it goes. So I'm not worried about whether I show it left or right. That doesn't bother me. But I do want to put it on there because when I'm going to prove that 0 is when I go sum of fx is 0. Then it'll come out to be 0. So I don't like mixing the analysis and the drawing the free body diagram. I just want to draw a free body diagram. I see a pin joint, I get an X and a Y force. That's as deep as I think about it. I slap it on there. I'll figure out that 0 later. That's not a problem. Okay.
I mean, with that logic, though, isn't point A and point D also pin joints?
No, point A is a cable,
Right.
and point D is a linkage.
The linkage would be connected with the pin.
But there's another pin on the other end. And if you go to that page before, we call out linkages and how to handle them. So on page 360 on the left top of the sketches. So I can identify that as a link. And these are good questions, but see what I'm seeing is there's a pin, there's a pin. That's a link.
Okay.
That pulls in the direction of the link.
I got you.
Y'all good? Now, had that connection been made differently, it's very dependent on how they make that connection. They ran pins to there and made a link, so that's why I know it's that way. Now, they could have made that connection differently, and I might have had to handle it differently.
Okay.
So we're ignoring an upward force from the bottom linkage?
Well, I'm analyzing the beam,
Yeah.
so that's why I'm not going down there. But I know the force in the.
For the beam, it's just on that edge, but
Yeah.
if you just looked at the linkage itself, you can see that there's 2 forces.
Yeah, that's true. If I'm analyzing the linkage, I got to focus on what I'm analyzing.
Yeah,
Is
and
that-
it's pressing down.
I assumed it was. Yeah, I'm assuming that's in the phase where it's pulling down. So but you're right. There's an up and a down. It just depends where
But
you.
we're just showing it from that armature.
Yeah, exactly, and that's important.
So if you did the armature and the linkage, then
That would be different.
Then
Yeah.
you'd have the,
You really have to define what you're looking at when you draw these things up. Yeah.
And we don't care about the weight at D? because
Weight
it's-
at D.
at the very bottom end.
Well, I'm putting what I did, and what I did is somewhat arbitrary, but what I decided to do was to say, I've got 2 pieces to this mechanism. I've got this piece, and I'll put its center of gravity here and put its weight there. And then I've got a beam. And my beam, I said, is here, and I will put the entire weight of the beam at its center of gravity. That's kind of how I chose to handle it.
Okay. Yep.
So, but there's different ways to have done that. I picked that way. Okay. We good with that?
Yeah.
Question? This is all good. I mean, let's get this figured out. It's good questions. All right. How about that stoplight armature there? Now, what I did, I zoomed in on the connection. So what I'm doing here, I'm zooming in right there and blowing that up. So it looks like that. Notice those bolts in there. You see 2. There's 2 more on the far side. What type of connection is that, and how will you model it? kind of connection you got there where it's bolted up? What is that?
Cantilever?
Cantilever is the term. Fixed connection, there's different words for it. Okay? So those bolts will not allow the beam to move up or down. They won't allow it to move left, right, and they won't allow it to twist either, right? Look at the size of those bolts. I mean, those things, if you ever seen one of these things in a big windstorm, you know why they use such big bolts. Those things, if wind really starts blowing, those things just start swinging around. So, you know, of course, they can't have a failure on these. They just, you know, it's not a, yeah, right, you just can't do that. So that's why those bolts are so big, and those bolts are meant to lock that thing in there, okay? And they also use probably a ductile steel here, so they get a little bit of give when that thing starts swinging around in the wind too, for that, okay? So really the only thing, you know, this thing has a lot of detail on it because there's so much stuff hanging off of it, unfortunately, but what you have there is a fixed connection. So there is a Y reaction at that bolted connection, there's an X reaction, and there is a moment reaction. It's a couple, okay? So right here, I call it MR for reaction, then I put the letter afterwards. So that's the moment reaction at E. Okay, and then I've got all these different weights acting down, quite a few of them, unfortunately. It kind of complicates the drawing. Y'all doing all right with that? Okay. And we want to get these right because, you know, you can't start calculating stuff until you get a decent free body diagram that's correct, you know.
On the moment clockwise, doesn't the weight rotate everything counterclockwise?
Yeah, it would. And the moment's going to have to resist that.
The resistance.
Yeah.
Okay, so it's opposite of the
Yeah, that's the reaction. But the other thing too, I had the moment clockwise just seeing that, but had I guessed wrong, and these aren't guesses, I just got a negative answer when I ran the numbers for what the moment is. It's no big deal, okay? You got to get the forces going on the right line, but you can guess them either direction. You can guess the couples either direction. You just get a negative answer if you don't guess correctly, that's all. Okay. So we doing all right with that? Yeah, question there?
Where on like the zoomed in picture where you can see the bolts, clearly, where would you like pinpoint point A?
Point A or E?
Or E?
That's a good question. I would put E right there. I'm sorry.
Because if you wanted to do another, then do like a whole other question, you'd be like, okay, now let's ask about the connection and the forces on the bolts. And
To some degree, right, because you have these situations where the theory here doesn't match what's going on out in the world, and I think that's one of them. It's a good question, but I think E would be kind of a large point, and I'm gonna find the moment, and then if I wanna go in and figure out these bolt forces, then I'll start looking at the offset of the bolts and all that. And yeah, maybe a more technical way to do it too. I think someone was saying right in the middle, and I think if, you know, to answer your question in a literal way, I'd put it right in the middle. Yeah, you know, as near as I could in the middle, that's where I'd put it.
Just
But
pick a center of gravity.
yeah, right. I mean, another situation you run into is like if you have a beam and you're supporting columns, we model the columns as a point load, but columns aren't points, right? They got width. They're really a little distributed load. But it depends on what you're analyzing. If I'm analyzing the whole beam, I probably don't need to make a distributed load on every column. You know, y'all with me what I'm saying there? I mean, you know, if you look at the width of a column, the forces would be a distributed load across the column. It's very similar to the question you just asked. So the way you analyze it just depends on what your goal, what you're trying to figure out, okay? And that's that's something to keep in mind when you start working. You know, this stuff, we're modeling stuff, but it's not perfect. Nothing we do is perfect. Don't get hung up on that, you know, when you're working especially. Just do a good analysis, throw a safety factor at it if you need to, okay? Get it built, make sure it doesn't break. That's kind of what we do, okay? I've seen a lot of different ways to analyze things that people have done that's different than I would have done it, but it came out fine, you know. All right. So, we good with that? right, so we'll get some bit of homework here to do. Now, what I've got here are some free body diagrams to draw. And they are in the packet, of course. And this is now the deal on this stuff is just pull the page out of the packet and draw the diagrams. That's all that I really want you to do. So it's 2 pages. It's 12A and B. So for the homework there, it's 12 pages, 12A and B. And we're doing 251, 252, 253, 254, 255. You can just pull those, put your work on those pages. So you can just take those sketches and turn them into free body diagrams. Okay, I don't need problem write-ups or any of that. Just work right off of those pages and turn those sketches into free body diagrams. One thing that is important there is I want you to dimension the angles. Dimension. Not spelling very well there. The angles. And what I mean by that is I don't just want an arrow doing that, a force. I want an angle. If there is an angle on there, I want that angle put on there, because that's an important part of being able to solve out a problem, is knowing the angles of the forces. And so this stuff will be due Wednesday. And that will be the 12th.
So if it's like reaction forces, like you said about a pinch weight,
Mm-hmm.
how they have the reaction, the y direction reaction force, and then do we have to draw that at 90 degrees both ways, or is that?
They should be 90 degrees apart from how you draw them, I guess.
But it's just, yeah, okay. So, like,
I don't think maybe
I don't think it cares if it's 90 degrees. If it's anything but 90 degrees.
Just if it's close and I can look at it and say it's 90 degrees, we're good. We good? All right. So hope you all have a good weekend.
There's nothing due on Monday, right, David?
That's right, yeah.
I think so, I looked on Google.
Correct, yeah. It's just this is due on Wednesday. No, nothing on Monday.